Welcome back. We are now going to teach you how to do NFA to DFA conversion. The general idea is that while NFA are compact ways to represent regular languages, they represent configurations attained after a input symbol in terms of sets of states. So if we represent sets of states as a state, then from an NFA, you can expect a power set of states to be extracted and explicated. When you do that, you can actually represent the moves of an NFA as an equivalent set of moves of a DFA whose states are the power set of the NFA states potentially. So let us see all that play out. Let us go back to the NFA third last is one example that we had studied a little while ago. We will go through this example in great detail and see how the NFA can be converted to a DFA, this NFA. So you can see that the NFA has multiple final states and it has a transition relation. And let's draw it out. So this is the third last is one, first last, which is the last, second last, third last is a one. And it uses an epsilon move. First, let us see what operations you can perform on an NFA. So you can step an NFA on one of the eligible moves it can make. So we can step this NFA from state I on epsilon, and then it will execute the delta move that is represented over here, which is going to be present in the epsilon move sense. Okay, so this delta table shows it as I on an epsilon going to S0. All right, so let us execute this, and indeed you get S0, but the answer is a set of states always. So set of states is 0. So let us step the NFA on 0, which is one of the moves here. And indeed it swings back to state I. So when you step it on 1, it also steps back to set of states I. So at this point, we will wonder how we can get the epsilon moves incorporated. That is coming very soon. And what you have is a concept of E-closure or epsilon closure, which was hinted at a little while ago, where in an NFA, when you move through a set of certain, even when you do not move and you want to pursue all the epsilon moves, you can close out the reachable states through epsilon. So when you do that for state I, you get state I S0. So essentially, when you poise an NFA on state I, it doesn't stay there. It leaks into I0 also, in addition to I. This is the high voltage analogy that I had mentioned. So when you want to accept or study the acceptance, there is a help function. And when you mention the chatty option for the accepts NFA, it actually shows you how the NFA marches through this set of configurations. So that help option is handy. So let us view this in context and draw this out again and next to it. So we actually see how the acceptance is being described. So you can see IS0 is reached in the sense that was already E-closed. And then when you consume a 0, it is, I guess, IS0 again. Then it is going to consume a 1, that it is going to go to IS0 S1. IS0 is attained through the 0, which E-closes, and S0 goes to 1, S1, and there is no E-closure after that. So this is a trace of the sets of states that the NFA would march through if you subject it to this string. We can further study that through interactive widgets like we had done before. And here we give you the option of loading two different NFA. This would be an N1 and N2. And third last is the same machine that we were looking at. And there is another machine you can study, ends in 0101. Let us give it a test string, 0101, let us say. And first last is a 1, second last is a 0, third last is a 1. So there is a potential acceptance. So you enter. At this point, the interactive widget opens up. And we are studying the N2 machine because that is what we have fed as the second argument. So let us go to N2 and see how the machine consumes symbols. Nothing is fed. This is an implementation where I didn't consider epsilon. So I'm actually looking at the first character. Having consumed 0, it is in state I0 and as I and S0. And then when you consume 1, 0, 1, you can see I is 0, S1 is reached. And then when you expand out to consume one more, I S0, S1, and then that goes to S2. So I is 0. So this state doesn't have a 0 move, so it drops out. S1 goes to S2. So like that, you can explore piecemeal how the NFA includes, we have not consumed all the strings. Yeah, we have consumed all the symbols. And further increase of the slider doesn't give you any more characters to pick out. So I S0, F, S1 is the final accepting configuration. Since it includes F, one of the split NFAs, the tokens reaches state F, and that is the acceptance. You could actually see this through animate NFA also. And that is very easy to plant here. And if you want, we can do that. Perhaps we will do it just for reinforcement. So we'll get the familiar animation sequence. Again, I will recommend that you go to overview and get the animation incantations and animate DFA is planted, but we can edit it out to make an animate NFA. So that's what I typically do since I keep forgetting how to plant these. So I'll change this to NFA and then animate NFA. And NFA third. And it gives you the completion, so you can click it at this point. The animation would be available, and then you type 0101, and then you animate. You can watch how the configurations go through. So epsilon closure and I is 0 and I is 0 S1 and I is 0 S2 and I is 0 S1 F is reached. So exactly like this trace was showing you. So how to mechanize this action? This is a very simple pseudocode that can be illustrated in a second. Let us do that. Okay, so the algorithm itself is spelled out here and illustrated in a with respect to a simple NFA. So the input is an NFA, such as here. The output is a language equivalent DFA. The method is subset construction. Add the e-closure of the initial state of the NFA as an unexpanded state of the DFA, D, being built. And this would also be the initial state of the DFA being built. So e-closure of the I is the initial state of the DFA. The e-closure of I will take you to I, A, G, but then also B and C, IA, B, G, C. So all these states are reached without consuming anything. And now what you do is repeat, choose a state S of D that has not been expanded. This is the only unexpanded state, and expand it. When you expand that state, you mark that state as expanded, so we don't do that state again. And if that state is not intersecting, intersecting final state, record it to be the final state. There is no final state intersection, so it is not a final state. For each symbol in the alphabet, for each state in the little unexpanded set of states, so the little states here. Move the state according to the delta of the NFA, and then perform the e-closure of the union of all the sets of states reached. So you move it according to the character from that state, and take that will be the SC set of states, union all the SCs for every start state that you march from. So you move it from I, move it from A, move it from B, move it from C, move it from G on a 0. You get little sets of states whose union is done, and you should check your work. So let us do that. If you move from I on a 0, you get nothing, no set of states. You move from A on a 0, nothing else. If you move from B, no set of states. You move from C, you get one set of states, which is set E. And then what do you get? Then from G, you get nothing. So you have set E. And then, so the E-closure of E is performed. So E-closure of E is E, A, G, B, C. E, A, G, B, G, C. Okay. So that is how you get this set of states. So that is what this E-closure results. If SC is in present in D, add it as an unexpanded state. So this has not been seen before. So you add it and add a move from the state being expanded to the state, to the D's transition. So we add this edge. And that is just the expand call until there are no more unexpanded states. So now this is not an unexpanded. So now you have to move it on every character. So this is not done yet. So we do it for 1 also. So for 1, you get this set of states. Let's read it out. I has nothing on a 1. A has nothing on a 1 in the NFA. B has D in the set of states. C has nothing on a 1. And G has F in the set of states. So we are now left with the task of E-closing D and E-closing F and taking their union. F has no E-closure, so F remains F. D has an E-closure, which includes D, A, B, C, G. D, A, B, C, G, and then F also is added. So that's how the expansion of this state is completed for every character in the alphabet. And then the call comes back until there are no more expanded states. So then this state will be picked up and expanded. So you would get the expansion recursively going through. And this is the diagram that emerges. So that is the algorithm that we will be implementing. And we can practice the NFA2DFA conversion by revisiting NFA.object, NFA third last again. Then when you perform NFA2DFA according to the algorithm I explained on this machine, we are including a state name max size, which is 40, so that we can actually see the real state names, which will be seen. If you don't do this, let us see what happens. So if I cut this out and remove this, and also cut this out and remove it, then it does the work. But look at the state names. They have new state names, ST0, ST2, ST1, that represent the set of states. So we want to see what these original states are. The reason I collapse is I don't want any really large and ugly state names. So if I were to reinstate these back and do it, then you get a machine that is much more informative. And let us read this machine in context with this machine. So indeed, we start with the E-closure of state I, which is I as 0 in this case. And I as 0 on a 0 goes back to I as 0 and it E-closes. Then I as 0 on a 1 goes to I as 0 S1, I as 0 S1. So the sets of states are now being named through the underscores. So this is the algorithm that I just now explained being played out. And let us try to do I as 0 S2, I as 0 S2. So S2 on a 1 would take you to F. So that is included. And S0 on a 1 goes to S1. There is no E closure. That is the S1. And you have to do I on a 1 back to I. So the set of states is Fi S0 S1. Since it includes a final state, you mark it as a final state before expanding again. So now you see how the NFA2DFA conversion works. And here's a trick to explicate the state names in the context of this machine. Okay. So since we are at this point, we can also revisit or visit, however you remember, Brasowski's DFA minimization. This is a way to minimize these machines. So since it's there in the same notebook, why don't I mention it? So reverse the DFA in question, determinize it using the algorithm we just now studied, reverse and determinize. So let us see what happens and perform it on here. So this is the unminimized DFA. Reversing a DFA is a function. It is available, and I don't need to run it. So I could run it piecemeal. So reverse of DFA of what? This is the blimp DFA. And that will be an NFA, because when you have two transitions that lead to a state on a same symbol, when you reverse, they become transitions going out. So they become non-deterministic at that point. So dot object NFA of reverse DFA blimp would tell you this is the reversed machine. So you imagine reversing every edge here, start the flows at all the originally final states and now called initial. So you see F2, F6 was a final and F2 was a final. Now F2 is an initial, F6 is an initial. So all these arrows that impinge on these edges were the original final states. And what is the real final state now? So we end up in a reversed flow, we end up in the initial state of the original machine. So that initial state of the original machine now gets treated as a final state. So this is just the reversal of this DFA. And reversal of a DFA contains or essentially is the language. The language of the reverse of a DFA is nothing but the reverse of the language of the original DFA, attained by starting from all these final states and ending up in I1. That would be the language of this NFA. Then you had to convert it to DFA, determinize it. So NFA2DFA of reverse of DFA of blimp. And we can dot object it. And then what you see is this machine. Wow, this machine is already the DFA equivalent of this NFA. And again, we can look at it from the full set of state name max size. So let me see with my cut buffer has it. Yes, it does. So I can put a state name max size here and see whether I see more. Well, the state names will be humongous because there are too many states. Maybe 80 will show it. I'm just trying to guess how much width I had to allow. If it doesn't work, you can figure it out later. Oh, indeed, it worked. See? So now you can see why I collapsed state names. So F2, F3, F6, F9, I1, S4, S5, S7, S8 would be a set of states present in this conversion. So now you see that all the sets of states reached can be studied. And the e-closure of F2, F3, F6, F9, F2, F3, F6, F9 is itself F2, F3, F6, F9. Doesn't have epsilon transition, so that is the initial state. Okay, so now if you just perform the whole thing in one shot, you get this machine, a pretty looking machine. And this is the minimized machine. And then when you minimize using the conventional method and do it using this method, the machines would be isomorphic, which I had seen. ISO-DFA of, I didn't call this something. This is called min-DFA blim. This is the min-DFA. So I can do ISO-DFA, min-DFA blim, and followed by min-DFA BRZ. That would return something. So min-DFA Brzezowski is as a single command. I don't know what this is, so I should evaluate this. Okay, so this is certain Jove something. So this is really not the DFA itself. So we can pluck out NFA2DFA, reverse DFA, NFA2DFA, reverse DFA of third blip. So that would be the Brzezowski equivalent minimization. And let's put that here and then make sure that I close enough. Okay, so at this point, the isomorphism test passes. So you get the same DFA in both cases. I guess this is a good point at which to end this NFA2DFA recording. And now you can revisit the points. The basic idea is the E-closure, epsilon closure, how you do it step by step. There were operations on NFAs that were introduced, and the operations on NFA were there as stepping stones, but really later on, you will not be implementing these operations or playing with them because it gets too tedious, but you can still retain the basic understanding. For pushdown automata and Turing machines, there isn't an equivalent non-deterministic to deterministic conversion. So while it is available, enjoy it, because for finite state machines, this conversion is available, and you might as well use it. And it can actually cause a blow up. We didn't see it in this case as we saw it in a certain sense. So this is the third last is 1, and its minimal form was 1, 2, 3, 4, 5, 6, 7, 8. And it will go even higher. If you want to see that, let us do one more, which is present here, I think. So this is the fourth last. Do I have it? Fourth last, let me check. Yeah, there is a fourth last is 1. So it adds one more. NFA fourth last is 1. And let us view this guy. So we'll view it at the end. So we can contrast the sizes. So we come here and add NFA fourth last is 1 dot object NFA of NFA fourth last is 1, and then option enter gives you a cell to add new comments, and now we can do dot object DFA of NFA2DFA of NFA fourth last 1, and let's give that. And that is pretty large. So you can see the blow up of exponentiality, and we can see how many states we had. We didn't want to just visually count it. So this is 1, 2, 3, 4, 5, 6 states. It grew from the previous by 1 state in the NFA. So NFAs have linear growth, but if you do length, if you do length of this guy, and the length of the final states of this guy, and come here, length of index the set of states and see what happens. That is 16. So you can actually see the doubling. Whereas if you do length of NFA fourth last 1 is Q. What do you get? You get 6. And how about the previous one? The previous one was NFA third last is 1, and it was not called TH last, fourth last. So let us see whether it was called third last, and put in the same name. Maybe it was written as THIRD. No, TRD, 3RD. So that is fine. It's a little typo. So NFA3, NFA3RD, last one. Do you exist? Yeah. So NFAs grew from 5 to 6, whereas the DFA went from 8 to 16. So you can actually see that if you go back to the original one, it is 8. Okay. So this finishes several concepts of the blow up possible. And also, you also see how Grozowski's algorithm can be built using these ideas. So thank you. And we will see you next video.